Question 2.8. When electromagnetic radiation of wavelength 300 nanometers falls on the surface of sodium, electrons are emitted with a kinetic energy of 1.68 into 10 to the power 5 joules per mole. What is the minimum energy needed to remove an electron from sodium, and what is the maximum wavelength that will cause the photoelectron to be emitted? Now, before we start all of this, let's first write out what has been given to us. We know that the wavelength of the particular electromagnetic radiation is 300 nanometer. We also know that the kinetic energy of the electron which is emitted is 1.68 into 10 to the power 5 joules per mole, because it's 1 mole of electron. We need to calculate the minimum energy which is required, and we also need to calculate the maximum wavelength. So the minimum frequency is the maximum wavelength. So the threshold frequency, if you have not checked it out, do check out the videos that we had done about the concept of photoelectric effect. It is to do with the concept of photoelectric effect along with the Planck's quantum theory and Einstein's explanation of the same. So first, let's calculate the energy of the photon. So energy of the photon, that is E equals to h mu. We know that mu is equal to c by lambda, so E equal to hc by lambda. So here we know h is 6.626 into 10 to the power 34 joules, minus 34 joules second. We also know that c is equals to 3 into 10 to the power 8 meters per second. We have been given the value of lambda, which is the wavelength. So 300 nanometers, which is 300 into 10 to the power minus 9 meters. Okay, so we are just substituting all of this. So 6.626 into 10 to the power minus 34 joules second into 3 into 10 to the power 8 meters per second divided by 300 into 10 to the power minus 9 meters. When this is simplified, we get 6.626 because 3 under 3, so you get 6.626 into 10 to the power minus 19 joules. So from this we calculated the energy of the photon. Next, we've been given kinetic energy of 1 mole of electron equals to 1.68 into 10 to the power 5 joules per mole. Then kinetic energy of 1 electron will be 1.68 into 10 to the power 5 joules per mole and divided by 6.022 into 10 to the power 23. So basically, since you're multiplying it, I'll just cancel the mole inverse, since you are dividing it by 6.022 into 10 to the power 23. And when this is simplified, we get the kinetic energy of the emitted electron is 2.79 into 10 to the power minus 19 joules. Now, we know when, so the basic concept is when light is hit or when photons are hit, electrons are emitted out. This is the basic concept of photoelectric effect. So, when you have, so the energy of the photon, so the total energy of the photon gets used up for the removal. So that's the binding energy, or this is also called as the minimum energy that is required, plus the kinetic energy. So the photon's energy is getting used in two ways. First, it is used for removal of the electron, that is the minimum amount of energy that is required, and the remaining gets used up as kinetic energy. So this is basically the minimum amount of the binding energy, is the minimum amount of energy required to remove an electron. And this is equal to, basically we are subtracting the two values. So that's nothing but 6.626 into 10 to the power minus 19 joules minus 2.79 into 10 to the power minus 19 joules. When this is simplified, we get 3.84 into 10 to the power minus 19 joules. Okay, so first we had to calculate the minimum energy that is required. So if from the minimum energy we can calculate the value of lambda. So lambda will be equal to hc by E. So h, as we know, is 6.626 into 10 to the power minus 34 joules second into 3 into 10 to the power 8 meters per second divided by 3.84 into 10 to the power minus 19 joules. And when this is simplified, we get the wavelength as 5.17 into 10 to the power minus 7 meters, or 517 into 10 to the power minus 9 meters, which is equals to 517 nanometers. So we were given the wavelength of the initial, so this lambda value is the lambda value or the wavelength of the minimum amount of wavelength that is required, maximum amount of wavelength that is required for the removal of electrons. So this question, first of all, to start with, involves the concept of photoelectric effect. We have been given the value of lambda of the incident or the electromagnetic radiation, and that was 300 nanometers, which is equal to 300 into 10 to the power minus 9 meters. Now we were also given the kinetic energy of 1 mole of the electron which was ejected out. From this we were able to calculate the energy of one photon, that's equal to h mu, and from there we were able to calculate the energy. And also kinetic energy was given for 1 mole. So from there we were able to calculate the kinetic energy of 1 electron. Whenever photoelectric effect happens, when the energy of the photon is higher than the required energy, it is used up for binding energy, or it is used up for removal of the electron from the surface, and the kinetic energy. So the minimum amount of energy which is required to remove one electron is given by subtracting these two values, and that gave us 3.84 10 to the power minus 19 joules. The calculation with decimal points was already discussed in chapter 1. If you haven't, do check it out. Next, we were able to calculate the value of lambda from the minimum energy that is required, because that corresponds to the maximum wavelength of the incident light that will lead to the emission of the photon, or the photoelectron. Question 2.9. The threshold frequency mu 0 for a metal is 7.0 into 10 to the power 14 second inverse, and calculate the kinetic energy of an electron emitted when the radiation of frequency mu equals to 1.0 into 10 to the power 15 second inverse hits the metal. So the kinetic energy is what we have to calculate, and we've been given the threshold frequency and the frequency of the radiation. Oh, don't you think it's lesser? This is only 1, this is 7. So obviously the frequency emitted is less, so there will be no electrons ejected, right? Think about it. Yeah. Here you have 10 to the power 15 and here you have 10 to the power 14. So this is technically 10 into 10 to the power 15. So this will have some amount of energy associated with it. And this in turn basically means that when this is taken into consideration, this is used up for two things. One is the minimum energy required for the electrons to come out. The second will be for the kinetic energy. So we need to calculate the kinetic energy of the electrons. Now, according to the Planck's quantum theory, using the Planck's quantum theory, Einstein was the one to explain the concept of photoelectric effect. And in his explanation, if you recall, we had an equation which said that kinetic energy equals to h of mu minus mu naught. So I think in the videos we learned it as h mu equals to h mu naught plus the kinetic energy, where we consider this as the threshold frequency. So h mu minus h mu naught will be equal to kinetic energy, and that when you take it out as common, you will get this value. So we have the value of h, that is 6.626 into 10 to the power minus 34 joules second. And so here we are writing 6.626 into 10 to the power minus 34 joules second into the frequency, that is 1.0 into 10 to the power 15 second inverse minus 7.0 into 10 to the power 14 second inverse. So by the rules and regulations that we learned about adding and subtracting, exponents and scientific notations, we know that we need to convert this into a common power and take it out as a common number. So here you can write it as 10.0 into, minus 7.0 into 10 to the power minus, 10 to the power 14 second inverse, and this second inverse can cancel with seconds and you'll get 3 over here, and this all of this is simplified, or let me just write it down, 6.626 into 10 to the power, so that you can understand, 34 joules into 3.0 into 10 to the power 14. Second and second got cancelled. Okay, so this gives us this value, and this is equal to 1.988 into 10 to the power minus 19 joules. So this problem was based on the explanation of the concept of photoelectric effect using the Planck's theory. It's just a basic equation. We have that equation, we substituted it. To understand better about this particular thing, you should you can go check out the video I did about the same. So in the next video, we will be studying about the atomic spectra. So do check it out.